Okay, welcome to the ICANX, this great platform every Friday. So all over the world, good morning, good evening, depending on where you are. So my name is Misu Kim. I'm an assistant professor of Seongkyungan University from Korea. So I will be served as a moderator together with Martin, Professor Martin Tuo from Iowa State University, our greatest friend, our greatest researcher. So the theme of ICANX talks this month, July, is the across nano divide. So last week we already had the amazing researcher Patrick, and today I'm very pleased to take the privilege to introduce Professor Haiding and Professor Jariwala. Both of them belong to the first cohort of our first 10 rising stars for this year, 2022. So you'll meet these amazing stars today. So next week and the following week, we're going to have Professor Min Kyu and Professor Oscar Martinez. And in the last week, we're going to have another Korean professor, Professor Takili from Seoul National University. So you enjoy all the across nano divide theme. So let me introduce our first speaker. So these are our great, amazing stars. So let me introduce our first speaker, Professor Haiding from the University of Science and Technology of China. He will share his research with us today for 40 minutes. Okay, so Haiding, the stage is yours.
Okay, great. Thank you.
Thank you.
So I will share my slides now.
Yes.
All right, can you guys see the slides and hear me?
Yes, very perfectly.
Okay, great, thanks. So, all right, thanks, Miso, for the kind introduction, and I would like to take the opportunity to thank the ICANX platform again for the wonderful platform for us, for the young scientists and the senior scientists to get together globally and to share some exciting researches with the community. So today I'm going to share our recent progress in some of the semiconductor devices, mostly focused on using the wide bandgap semiconductors for making optoelectronics in the deep UV band for light-emitting diodes as well as photodetectors. So I'm Haiding. I'm from University of Science and Technology of China. And so I will go with my presentation with 4 parts. First, I would like to introduce what is wide bandgap semiconductors, particularly, which is quite hot material right now in the so-called third generation semiconductor, gallium nitride. And then we use the gallium nitride to make high efficient light emitting diodes, LEDs here, as well as we will make those gallium nitride materials to make some efficient and highly detective photodetectors. Then I will conclude my talk. Okay, let's go with the first introduction about what is gallium nitride. Just give you a quick background, and you may know those kind of light bulbs, right? You can buy it maybe back to 10 years ago or 5 years ago. You can buy those kind of light bulbs at home or in the supermarket. But right now, you may be or may not be able to see them anymore because people are making very efficient light bulbs instead of using those old and conventional and traditional one, which is so-called LEDs, light emitting diode. And those are highly efficient light emitters, can combine with many color of phosphorus to convert the light into white color, blue color, or green, or whatever color you want. And so by combining, give you an example, if we combine the blue LED with the phosphor or yellow phosphor, we can generate white light as the same as the light bulbs we normally buy back into 10 years ago or even older, right? So due to the invention of the blue LED, actually those blue LEDs are made of so-called gallium nitride, okay? So those are due to the invention of the blue LED, 3 Japanese professors were awarded Nobel Prize in Physics back in 2014, and because in the invention of those efficient light emitting devices. So that's just give you a quick impression about what is gallium nitride and why we use gallium nitride. And not only gallium nitride can be made can be used to make those light emitting diode or LED bulbs. We can use it to make lasers. We can also use them to make power switches or power electronics. We can also use them to make power amplifiers and in the radar or in the many complicated systems. So this gallium nitride material is very powerful and very popular right now, and not only in our daily life but also in military applications. So it's very hot and quite useful material. So what is gallium nitride? And in gallium nitride, we normally in the group 3 nitride, gallium nitride is one of them. Okay, in the group 3 nitride family, we have aluminum nitride, we have gallium nitride, we have indium nitride. By combining them together, we can make all kinds of alloys or compound alloys, and then we can make and cover the entire spectrum band from the deep UV around 200 nanometer to infrared. As a result, so because of the we can change and direct band gap from covering 0.7 to 6.1 electron volt, and those materials can be doped into N-type and P-type. As a result, we can make all kinds of light emitting or photo optoelectronic devices, and those materials can heteroarchitecturally grow on many kinds of substrate. Exciting, and those kinds of such as silicon carbide, sapphire, and those materials have very high thermal conductivity. Importantly, those materials is not like silicon. Sometimes silicon is very easy to be etched by the chemical and get oxidized, but for gallium nitride, it's very robust. Or the nitride material is very robust. They have very high chemical resilience and radiation hardness. And those kind of material is like a stone. Okay, it's very environmental friendly. It's not toxic. So it's a material that we can use to make all kinds of devices. And that's our goal. Why I want to work on those material. But for example, in our group, and we make all kinds of devices, optoelectronics, like UV LEDs, UV laser diode, and UV photodetectors. That's our goal, is to use gallium nitride to make the deep UV, deep ultraviolet band from 200 nanometer to 380 nanometer. This within this broad band, and we are able to generate all kinds of UV devices. And those depend on their wavelengths from 200 to 80, 280 to 315, and 315 to 400. We can use their different light emitting energy, the photon energies. We can use them for water purification, disinfections, inspections, or for optical therapies, or for UV curing, and so on and so forth. It depends on the photon energies. So there are many applications in our daily life for those kind of UV optoelectronics. And in the system level, we can use those lights, UV light, for photolithography, for space exploration, for industrial use. So there's a lot of applications waiting for us to explore by using those kind of UV optoelectronics. And particularly, just give an example that due to the COVID-19, we are troubled, okay, by those diseases or by the viruses. But it's sad to see so many cases and deaths caused by the COVID-19. But scientists already discovered that just within 1 second exposure of those COVID-19 virus by the UV light, by the deep UV light, we are able to kill them 99.9%. Basically, there's a globally in the global health organization, they have already discovered and make a claim and a statement that by exposure those virus, okay, by the UV light, we are able to kill them quickly. So in our group, we have two major research. One is how we are able to make efficient light emitting devices, and in the next, I will talk about details how we are able to make it. And just give you a quick background: is the deep UV LED market is booming quickly. Okay, especially due to the breakout of the COVID-19. Everyone knows that we are able to kill those bacteria by using the UV light. And unfortunately, right now the UV light is still, by using the gallium nitride technology, is still quite poor. The efficiency is quite poor, but the market is booming. Okay, we expect it to grow very quickly, and we need high efficient UV light sources and energy efficient, environmental friendly. Conventionally, you are maybe familiar that people may use the alcohol, chemicals, heat to kill the bacteria. And a lot of people are familiar with that. We can use the mercury-based lamp. It will generate UV light, right? But those materials, the mercury lamp is very toxic, it's fragile, and the lifetime is very short, okay? The efficient, it's like conventionally we use the light bulbs, right? Light bulbs is very energy efficient, and it's waste a lot of heat, by generating a lot of heat, right? It's the electricity, not all electricity was converting into the light, but in the UV, it's the same thing. We wanted to make very energy efficient UV LEDs to replace those mercury lamps, to make them more efficient, energy efficient, and robust. That's our goal. And we wanted to make it very like a tiny and compact and a very long lifetime to compete and basically to replace the very old technology, so-called mercury lamp, to generate the UV light. But unfortunately, due to the material-wise and the device problems and challenges, and when we move to the shorter wavelengths, the efficiency drop significantly. When you go to the deep UV band, most of the efficiency or the wall plug efficiency, how much electricity was converted into light is less than 5%. This is totally not satisfied. We wanted to improve it. So there's a lot of ways and a lot of challenges need to do. And we wanted, based on the wall plug efficiency, the definition is how we are able to generate high internal quantum efficiency, high current injection efficiency, and high light extraction efficiency. Those are all key important parameters to be improved in order to make or generate very efficient UV light by the light emitting diode. So our goal is to focus on this device and try to improve it from material-wise, how to grow high-quality material, okay? How to innovate the growth technology to make high-quality materials as well as high-quality epitaxial growth techniques and process, optimize growth conditions to make efficient device. Second, how we are able to optimize the device architectures, or we so-called chip geometry, to make efficient devices. Lastly, internally, we have to optimize, for example, how we are able to generate more photons out of this device and in the quantum wells, because in the quantum well, we generate the photons, right? So how we are able to optimize the device structure. Those are the works we have done in the past few years in our group, and I will discuss one by one in details later. So first of all, I will go to the epitaxial growth. In the epitaxial growth part is how we are able to generate efficient devices by using very unique substrate, so-called high miscut sapphire substrate, as well as we try to hybrid sapphire substrate with different materials to improve the light extraction efficiency, so-called we use a hybrid, okay? The definition of a hybrid will come later when I introduce our work. So first of all, why we introduce miscut sapphire substrate? Why we not use just regular sapphire substrate? So just give you an idea that for the blue LEDs right now is very highly efficient. The efficiency is like more than 60%. So why the blue LED is so efficient and our UV LED is like just 3 to 5%? Why? Because naturally, when we synthesize or grow the indium gallium nitride quantum wells, indium and gallium have very different in their atom size. As a result, when they come together and form thin films, naturally they will have form phase separated. So basically, this is a schematic illustration. When they form the indium gallium nitride thin films, they are separated. They have clusters inside the structures. As a result, they will generate so-called compositional inhomogeneity. The materials is uniform, is not uniform. As a result, we will be able to generate so-called potential fluctuation. The carriers, when they come into like the electron hole pairs, when they come into the quantum world, they are not be able to migrate. The only way they can migrate is to recombine together to generate light. So that's why the blue LED is very efficient. However, when we come to the aluminum gallium nitride quantum wells, because this is the quantum well where we can generate UV light. But unfortunately, the gallium and aluminum atoms, they have very close atom size. Basically, their atom size is very close to each other. Okay, unlike the indium and the gallium, they have big difference. As a result, for most of the aluminum gallium nitride quantum well, you can see the quantum wells are very flat. Okay, it's very uniform in the chemical compositions. So as a result, we cannot have very high potential fluctuation, also called compositional inhomogeneity. So what we have introduced, we introduced a very highly miscutted sapphire substrate. You can see this is a substrate. So we have the steps. As a result, when we generate quantum wells, like in the flat substrate, there's very flat quantum wells and very super smooth. But in the miscut sapphire substrate, we are able to generate a little bit of step bunches on the green boundary, and it's like you can see there's a wavy quantum wells. These wavy quantum wells cause the material in compositional inhomogeneity, and we artificially create so-called potential fluctuation inside the quantum well. Surprisingly, what we learned and we discovered that by using the miscut sapphire substrate, we are able to increase the light output power significantly by 10 times, and we achieved almost nearly the very highest internal quantum efficiency in the world by using this technology, so-called using the miscut sapphire substrate. And the reason is because at the room temperature, we measure the lifetime of the carriers at the radiative recombination. For the example, grow on the miscut sapphire substrate or 4-degree miscut sapphire substrate. This is very long than compared with the lifetime for those film grow on the flat sapphire substrate. And we compare the light output power, and the light output power will nearly double output power compared with those on the flat sapphire substrate. And we did a calculation that found that it is the compositional inhomogeneity caused in the quantum wells and lead to the increase and significant increase of the quantum efficiency. Okay, that's one of the work, and our work was highlighted by the respected magazine, so-called Compound Semiconductor, on the cover, and the editor, the chief editor, Dr. Richard was also mentioned that our work is a breakthrough in the deep UV. And next is we will introduce the hybrid nano pattern sapphire substrate. Normally, we use those kind of patterned sapphire substrate, but the sapphire substrate and the gallium nitride, when the light coming out of the nano pattern sapphire substrate, it's not easily to be extracted. The photons are not easy to be extracted. By hybriding a silicon oxide, introducing a silicon oxide on top of the sapphire, and to form those hybrid nano pattern sapphire substrate, we are able to introduce a different refractive index. Due to the refractive index contrast between the silicon oxide and gallium nitride and aluminum oxide and gallium nitride, the UV light can be extracted more efficiently. As a result, you can see the red curve shows that when we introduce the hybrid nano pattern sapphire substrate, we are able to extract more significant light out of the sapphire substrate in comparison with a regular conventional pattern sapphire substrate. The reason behind it is this: the critical angle of the total internal reflection at gallium nitride and sapphire, as well gallium nitride and gallium silicon oxide and sapphire and air interfaces, has specific angle. And due to the introduction of the silicon oxide pattern, which is smaller than those sapphire layer, there's no internal reflection. As a result, more light can be extracted. Basically, the light extraction efficiency for the hybrid sapphire substrate is much higher than for those conventional one. Okay, so first we introduced the architectural growth techniques on the miscut and hybrid sapphire substrate, but I would like to introduce now is how to optimize the chip geometries. And for example, we introduce single micro LED structures and to improve the light extraction as well, and see how it goes. So first, what we do is we change the diameter of the chip. And the diameter of the LED decrease from 300 microns to 200 to 20 microns. Okay, when we decrease, what we learned that is that current density significantly increased in the smaller size of the chip, and also the external quantum efficiency is also higher. And what we compare those devices among with them between different diameter of the device, the peak internal quantum efficiency can increase by 20% if we decrease the chip size, and the peak current density can be boosted from 5 M per centimeter to 99 M per centimeter. Also, we observe strong red shift and increase of the 4-Weiss half maximum of the spectrum, and due to the self-heating. So the conclusion is a smaller LED will have a higher current density, a higher power density, and a higher external quantum efficiency. And to optimize each device, right? The device is here for each of the micro LEDs, but we have to optimize it. So the one critical aspect is to improve the sidewall angle. See, when we etch the devices, make those devices, we need to etch them to expose the uncontact. So what we have done is we compare the device with vertical and with the inclined sidewalls to compare them. What's the device performance? And what we learned from here is the inclined angle has a significant impact on the light output power. And what we learned that here is with inclined angle, we have much higher output power. And we compare them, and what we learned that inside the wall can enlarge the external quantum efficiency, and especially when compare the size of device. Okay, compare with the 20 micron device with 40 micron device. The smaller the device, the larger EQE, and the smaller device, you can see that the smaller device has much higher impact, and the sidewall angle has much higher impact compared with the larger device. You see, in the 20 micron, we can have, with the inclined angle, we have much larger improved external quantum efficiency compared with 40 micron in size. So we performed the optical calculations to learn why we have such higher light output power compared with the device within the device. And we learned from here is that the chip size has a significant impact on the light extraction efficiency, and the angle also has very high impact on the light output power. And there's an optimum angle, which is from 25 to 35 degrees, and is more beneficial for the light extraction. And for a single device, okay, if we make those micro scale light LEDs as we made here, a single device, but the single device normally is, the performance for the single device is limited because its power is only from a very small chip. So what we have to do is we make them into arrays, okay? Make them into arrays. When we make those micro LED arrays, we are able to generate high power. That's what we learned that here is a regular big chip size, okay? 200 micron in size. This is a regular chip size. And once we make it into a smaller chip size into array with same light emitting areas, and we found that the smaller the chip size, using the micro LED arrays have highly improved light output power. That's what we learned, that the almost, okay, compared with the regular LEDs with 200 micron in size, our micro LED arrays has more than 52% light output power compared with the regular conventional device. Also, we have 22% higher peak external quantum efficiency compared with the regular big chip. So basically is we make a smaller LED and put them into array. It's better solution. This is a better solution compared with a conventional regular big chips. So it's better for us basically is to make micro LED arrays. We are able to have a higher light output power, higher external quantum efficiency. And so we did the optical calculations to learn why we found that in the center as well as at the edge, both with smaller size arrays, we are able to have much higher light extraction efficiency. As a result, in total, when we measure the device in our system, we found that the total output power in the micro LED arrays is much better, higher than the regular big chip LEDs without array. And we found that the far-field pattern measurement also showed that the micro LED array possesses a better forward directionality of the emission as well. And lastly, we also make a different geometry of the devices by making nanowire LEDs rather than as thin films. And those nanowire LEDs, you can imagine that each nanowire can emit light. So due to the light can be scattered around those nanowires, we are able to extract more light out of those nanowires. So we fabricate them into the device like this way and put it into the microscope to measure the light out of power. Surprisingly, we found that when we increase the light in current injection, the external quantum efficiency was continuously increased with so-called droop-free behavior. And the light out of power, once we passivate those nanowires by some chemical treatment, we are able to reduce the turn-on voltage. Meanwhile, we are able to increase the light output power. Okay, so in the last part, we will continue to optimize the light device structure. Previously, we optimized the growth conditions and the growth techniques, and we also optimize the chip geometry. But internally, we have to also optimize the device structures, right? Including how we are able to optimize quantum well quantum structures, and we use different structures to improve the quantum efficiency. So that's what we have done is we introduce some unique quantum well structures. For example, here, we normally use flat quantum wells. Now we use the tilted, so-called compositional changed quantum well, excuse me. So by suppressing the polarization effect in those nitride films, we can improve. See, the red curve shows that by using those tilted quantum wells, we are able to have much higher light out power. And the reason is that by conventionally, people use aluminum composition is constant, like this way, is flat. And when we change the aluminum composition, linearly decrease, and another composition is linearly increase. What we learned that the wave function overlap, this one is 40%, this is 33%, this is 58%. So basically it's more electron hole pairs, they can recombine together to generate light. So basically a linearly graded aluminum composition in the quantum well can control the intensity of the polarization field in the quantum well, thereby increasing the overlap rate of the electron hole wave functions. So as a result, this quantum well structures can, with linearly increased aluminum composition, has the best performance, which is mainly due to the substantially increased overlap ratio of the electron hole and wave function overlap, as shown in this red curve. So once we optimize the quantum wells, we also have to optimize the quantum barrier structures because barriers also play a critical role here. So this is the way how we change the quantum barriers in our device design. And what we learned that for those quantum barrier structure in the active region, the structure with gradiently increasing aluminum composition is proposed. And we learned that from the red curve that it shows most higher external quantum efficiency. This is because we reducing the electron leakage by increasing the gradient. We gradiently increase the aluminum composition, and we also increasing the hole injection efficiency. Lastly, we also improve the performance of the UV LEDs, and this is because we can enlarge the electron barriers and decrease hole barriers in the electron blocking layer for the DPUV by incorporation with such very unique graded quantum barrier structures. And lastly, we also changed the quantum barrier, in particular in the last quantum barrier, because the last quantum barrier is very close to the electron blocking layer that plays significant role here. And it's very critical as a bridge connecting the active layer and the hole injection layer. It can effectively reduce the leakage current from the left to the right. As a result, the increase while we can increase the hole injection efficiency, thereby we improve the luminescence efficiency as shown in the blue curve here. And this is the deep analysis why from the band engineering diagrams, we are able to diagnose why in this device has better performance compared with this one. So the large quantum barrier indeed play a very critical role here to avoid, basically to reduce the current leakage and while to improve the current the device performance. And this is eventually the EL performance of the device. And indeed, the device B has a higher, with a unique barrier device, we are able to have much higher device performance. So overall, we were invited to write a review report about how we are able to design the band structures, basically the band structure of the LEDs to strategically to improve the performance. And we, in this review paper, we introduced many strategies about band engineering designs, and we summarize and propose an energy band diagram method to improve the optical performance. And also we make the device architecture to be very unique. You can see this conventionally, you have a PIN junction, okay? PN junction for making a simple diode. But what if for each device, like you can see that the emitting area is limited. What if we connect two devices into one device, as you can see from the right? What do we learn that when we connect these two devices by using a tunnel junction and they are interconnected, you can see from this band diagrams, by including the tunnel junction, and we are able to stack two devices into one device. And as a result, what we can see is the light output power was doubled, okay? Was doubled compared with a conventional one. And simply by increasing the number of quantum wires is not enough, okay? What we have done is we cascading two active regions with a tunnel junction can greatly improve the performance of DPUV. This is mainly due to the multiple injection and the recombination of the electron holes in the active region. And as a result, you can see the light output power can be significantly improved when we cascade two LED together onto one device. And the last architecture renovation is we put a LED together with a photo detector. So what we have done is usually in a device, a lot of electrons are wasted. A lot of photons is wasted, cannot escape from the device. So we basically put a recycle, light recycle here, photon recycle, okay? Basically, we recycle those wasted photons and regenerate electron hole pairs. And as a result, we can see that this is the electron luminescence of the device. And when we inject the current and voltage together into the device, and what we learned that by those, by comparing the device with a regular one LED and with this very unique photo multiplier converters connected with a regular LED, we are able to, when we have the same light output power, but we just need a very little amount of current. So the quantum efficiency is very high, okay? Compared with the conventional one is only 0.36%. Now we have 21%. And this is the IV curve of the device. And this is a band diagram of the device. And what we learned that in the conventional one, in the new design device, we have much higher density of the holes inside the quantum wells. And what we learned that this mechanism of ultra high conversion of the LEDs at very low current is because with the introduction of the multiplicative magnifications inside this device, and the electric field in the photo detectors, which contribute to the collision ionization in the depletion layer, obtaining very high gains of even hundreds of times higher hole concentration. And this hole will go into the active region to recombine with the electron and generate light. As a result, we achieve very high wall plug efficiency. Basically, there's 4 steps. This is the first one: electron hole pairs combine in the quantum well and producing UV photons. And secondly, the photons are absorbed in the MPC structures and transformed into new electron hole pairs. And those new electron hole pairs are multiplied by the collision ionization in the MPC structure. And this multiplicative cavity is re-injected into the quantum wells to combine with the electron hole pairs and to generate electron to generate light. As a result, we achieve one of the highest wall plug efficiency for the deep UV LEDs. All right, so I have finished up with UV LEDs. Now I move to the next section about the photodetector. I will just quickly go through what we have done in the photodetector. And photodetector is very common. It's just convert light into the electrical signals, and those photodetectors can be used in the photolithography, in the space exploration, and so on and so forth. And people use those photodetectors for a lot of applications. And we use many kinds of materials for the UV photodetectors for gallium oxide, zinc oxide, gallium nitride as well. So in our group, we grow nanowires. The nanowires can absorb light much more light easily because due to the light scattering. Unlike thin films, a lot of light will be reflected back, right? But in the nanowires, once the light comes in, it will be absorbed immediately in those nanowires. And there's a large surface to volume ratio for light absorption. And the nanowires can easily be decorated and modified. As a result, we are able to tune the carrier transport behaviors in those nanowires. So conventionally, and people already did a lot of work by using those nanowires for photoelectrochemical applications due to the strong chemical stability of the gallium nitride and the tunable band gaps. And if we put the gallium nitride nanowires into aqueous or electrolyte, what we can learn is this. Once we put them and the nanowires are illuminated with the light, photo excitation will generate electron pairs. And there will be radiative recombination, and there will also be non-radiative recombinations as a result here. But a lot of electron photons, electron hole pairs, once we generate them by illuminating those nanowires, we will cause upward or downward band bending, depends on whether this is P-type material, this is N-type material or P-type material, once we expose those nanowires into the electrolyte. So we generate and construct such a photodetector, so-called photoelectrochemical type detector, PEC device. So basically, once we make those kind of nanowire to absorb the light, and with the downward band bending as the driving force, the photo-generated electron drift to the argon nanostructures and undergoes the redox reaction. And in the step B, once the band bending induces direct transfer of holes towards the opposite direction of the PT counter electrode participating in the reaction. In this case, we will record this as a photocurrent. So we are able to make a very high efficient solar blind PEC photodetectors, or we also make into PIN junction, and we also make a dual band PEC type photodetectors. Also, we use the plasmonic effect on those nanowires to make broadband PEC devices. So I would like to introduce one important device we recently work on is a PIN junction. PIN junction is very clear, is we can only have unidirectional photocurrent. It's basically because this is this is PIN junction principle, is only one direction current can pass through the PN diode. However, what we are able to get is we create PEC type photodetectors by using a PIN junction here, and by illuminating with 254 nanometers, we are able to generate a negative photocurrent. Surprisingly, we illuminate this nanowire with 365 nanometer, we are able to generate positive photocurrent. So this is so-called bidirectional photocurrent in a PN heterojunction nanowires. We are able to generate two different kind of photocurrent. So this is the working principles about how, I will not go into the details, but basically is on the 254 nanometer, the gallium nitride this nanowire will generate the negative photocurrent, and this is the working principles. And then under 365 nanometer, only the bottom part, okay, only the bottom gallium nitride will absorb the light, generate the photocurrent. This photocurrent is positive. So there's a competing between the P-type and N-type materials. It depends on what kind of photons is being absorbed and what kind of reactions, whether this is HER reaction or whether it's OER reaction, will generate different type of the photocurrent. Okay, so I will not go into the details, but the result is at the 254, we have negative, and we have positive at 365 nanometer. And this kind of PEC devices can be used for a lot of applications in bio-related application, optical communication, optical logic, imaging, and wavelength discriminations, and so on. So I would like to conclude my talk today. So in our group, we will make high efficient light emitting diodes or laser diodes. We also make very highly detective photodetectors made in PEC type. And the key is to have how we are able to control the carrier generation, carrier transport and control. And especially we have to grow high quality materials in terms of thin films or nanowires, and then fabricate them into the device. So we can also integrate different devices onto a single platform as well. Okay, finally, I would like to conclude and thank you, and thanks our group members for the hard working. And with any questions, I'm happy to take any questions. Thank you.
Thank you, Haiding. Maybe you can stop sharing.
Okay.
So that I will go too deep, and then we'll have questions at the end.
Okay.
All right. So thank you, everyone. And our next speaker is Deep Jariwala. Deep is an assistant professor at the University of Pennsylvania, the Department of Electrical and Systems Engineering. He got his BS in IIT system in 2010, PhD in Northwestern in 2015, and then moved to Caltech as a Lesnick postdoctoral fellow. And then after that, he started his career. He has many awards. I'm not going to go through all of them, Deep. I would like you to share your science. But just as a highlight, recently he got the International Union of Vacuum Science Technology and Application, EBARA award. Not the first one from that society. I think it's his second. He's also been listed in Forbes 30 under 30. He's a young investigator awardee from AMI Research Office. He's an Intel Rising Star, and of course, is our very own ICANX Young Scientist awardee. Deep, I'll hand over to you.
All right, thank you, Martin. Let me see. Okay, so are you able to see my screen now?
Yep.
Okay, very good. So you go full screen, and then laser pointer is on. So yeah, well, thank you so much, Martin, for the very generous introduction. I really appreciate it. And thanks to Alice, Miso, and everybody else in the ICANX team for providing me this great platform and opportunity to discuss some of our research. So as the title of the talk goes, I'm going to talk a little bit more fundamental as opposed to the previous talk, which was very exciting, very applied application of the optoelectronic semiconductors. I'll be discussing more fundamental, more basic science of strong light matter interactions in not bulk semiconductors, but atomically thin semiconductors, such as chalcogenides, as you will see soon. So before I get started, let me give a very brief overview to all the research that we do in our group. So our group is about 4.5 years old now at the University of Pennsylvania, and we work in many research areas. So we have a broad range of research interests. A large part of the group actually works on nanoelectronic devices. This is low power logic and memory devices. And I'm not going to be talking about that research today. Maybe in another opportunity at ICANX, I can discuss about it. What I will be focusing on today is this part of the group, which is group's research, which is nanophotonics and optoelectronics, which is where we study fundamental light matter interactions in novel low dimensional semiconductors, and also thinking a little bit about how to convert them into devices, though not predominantly focusing on that. The other two areas in the research group are regarding functional imaging, and this is an area where we do both near field imaging using an SNOM type technique, as well as electron beam based imaging in an electron microscope. And the last area, which is more on the synthesis of new materials, namely metal organic chemical vapor deposition for growing chalcogenides, and also more recently we are into nitrides as well. So as you can see, this area of the group has been most productive in terms of the number of publications and exciting results. So I will be focusing my talk today on this area. So to get started, let me give a very brief and broad overview about what I like to call as exotonic quantum materials. Now, I know that the word quantum technology in general is highly used or in some cases also abused, but if you want to think about quantum confinement in materials, these materials that I'm listing on these slides are actually very well known. And one of the features in semiconductor materials that becomes very pronounced when you confine them in, or you quantum confine them into any of the dimensions, is that excitons start dominating the optical properties of those semiconductors. Now, this has been very well known for a very long time. And the most popular example of this, which has actually made it into commercial market, is the one that was presented by the previous speaker, or similar types of materials known as 3-5 semiconductor quantum wells and quantum dots. In these materials, the effect of excitons and their amazing properties, both in terms of luminescence as well as optical modulation, has been studied for over 30 years now. But what has happened is that people obviously have a penchant for making things cheaper, making things out of newer materials that are more easy to deal with, more easy to process. And so various other types of excotonic quantum materials have been looked into. Some of them are very popular, such as organic small molecules and polymers. These are also commercial in the form of OLEDs, as we all know. But then there has also been a lot of research on colloidal nanocrystals. These are the cadmium sulfide or cadmium selenide based quantum dots. These are also something that are quite popular and have been commercialized in the form of QLEDs. Some of you may have seen QLED TV out of LG or Samsung and so on. But there are also other types of low dimensional exotonic quantum materials that have been heavily investigated. Some are these one dimensional ones, such as carbon nanotubes, are also something that many of you may remember, which have been very heavily investigated. What my group likes to focus on are of the more recently emerging these two-dimensional materials. And in particular, we like to focus on two-dimensional transition metal chalcogenides and phosphochalcogenides, as well as halide perovskites. Okay, so I will be focusing most of the talk on these materials, though I should mention that my group also works on these materials over here. And due to lack of time or lack of focus, I won't be discussing them as much. Okay, so to get started, why are excitons in this 2D transition metal dichalcogenides, TMDCs as we are called, they are quite exciting, and why are they important? And further, what can you do with them? So to give you a very brief sense, exciton is formed whenever light gets absorbed in a semiconductor. But when you have these low dimensional semiconductors, such as the dimensionality is confined to say 2 dimension or 1 dimension, then the electrons and holes can interact very strongly after the light absorption via the electric fields that are penetrating out of the material, right? And so this leads to the properties or the optical properties of the material being dominated by the excitons, as opposed to free charge carriers, which are normally formed in all bulk materials, such as silicon or gallium arsenide or gallium nitride, which was being discussed in the previous talk, right? And so in low dimensional materials, excitons dominate these optical properties. So you can see that the optical absorption is dominated by excitons, and the actual band gap is much further away. Now, in layered systems, even when you have multiple layers, because the bonding in plane versus out of plane is so different, you still have excitons dominating most of the properties as opposed to the bulk band gap, right? And so this makes these materials quite interesting and their optical response quite interesting as opposed to other three-dimensional materials which have isotropic bonding in all 3 dimensions. The other interesting thing that happens with excitons in these 2D systems is that as you apply a voltage to the material and you populate and depopulate charge carriers into it, you can actually move these excitons or change the excitonic response quite dramatically. In fact, it was shown a few years ago now that you can modulate the refractive index in these materials by as much as 40 to 50%. That is a lot of modulation or electro-optic modulation as a function of electric field or changing carrier density. And to give you a sense, when you want to compare it to, say, silicon or gallium arsenide or any of the other bulk materials, they have less than 0.5%, sometimes even less than 0.1% change. And here we are talking about 40–50% change in the optical constants as a function of applied electric field or changing carrier density. And this makes it quite interesting for new types of optical modulator devices. Okay, so what we are interested in our group is looking at coupling between these excitons, which are excited states formed when light is absorbed in these low-dimensional semiconductors, and photons, which is nothing but light particles themselves. And so why are we interested in studying this? Well, there are a few reasons. There are fundamental reasons as well as applied reasons. A fundamental reason is that when you have a material that can support exciton, and if that material is, say, confined in a cavity which can be any box-like structure, where you also have a photon moving around between mirrors in that cavity, and now that photon energy is resonant with the exciton energy, then under certain conditions, you will form a state which is hybrid between photons and excitons, okay? And this state is typically known as Acetone Polarity. So it's a half light, half matter state. Very unusual, but this is what quantum mechanics leads to. You have a superposition of the wave function between the exciton and the photon, leading to hybrid light matter states. These kind of hybrid light matter states have been investigated for many, many years. And they have been known to also undergo some interesting fundamental physics, such as condensation to form Bose-Einstein condensates and things like that. And people have investigated these things in notably 3-5 quantum wells. And the subject of the investigation was to look for what are known as polariton lasing devices. And there have been theoretical predictions that some of these polariton lasing devices could operate at very low thresholds, which means they would require much less energy to operate as opposed to the standard photon lasing devices. And therefore, there has been a lot of interest in them. What has happened, however, is much of those studies have been limited to low temperatures. And that is because the binding energy of excitons in three-dimensional materials is much smaller, which means you really have to cool down these three-dimensional materials, such as 3-5 quantum wells or even other 3D materials, to actually see some of these exciton-related effects and exciton polariton effects. As opposed to that, in 2D materials that I talked about, the binding energy is much larger. So now you have these effects possible at room temperatures. The other exciting thing about these 2D materials is that you can peel them off. You can separate them layer by layer because of van der Waals nature of the bonding, as we have seen before, right? These bonding between the layers is quite weak. It's van der Waals. So you can separate them out. And so now you have basically isolated or separable quantum wells. These separable quantum wells can be put in any arbitrary optical cavity. This could be a plasmonic cavity, this could be a photonic crystal cavity, or what have you. You are not limited to this dielectric Bragg mirror-based cavity that you normally make via epitaxial growth, right? And so this has led to an explosion in research in coupling of excitons with photons in different types of optical cavities using these two-dimensional semiconductors and making all those measurements further at room temperature. There are several groups that have worked in this area. Of course, I'm not listing all of the groups. If I'm missing out your favorite group, please, I apologize. I have made sure to cite all of those groups in this review paper that we published earlier this year, where we have summarized all of this research that has happened over the past 5 to 8 years or so. Okay, so moving back to the idea of TMDCs and looking at excitons in them, how did we get interested in it in the first place? Well, the first place we got interested in them is just by looking at the band gaps and where do they lie in the energy spectrum. So, this is our standard prototypical material, which is, let's say, molybdenum disulfide or tungsten diselenide or something like that, right? And so you have these metal atoms, which could be molybdenum or tungsten, and then you have chalcogen atoms. So that is the basic structure of these materials. If you look at their band gaps, they're actually very well positioned in the visible part of the spectrum, right? They are also actually quite well positioned in terms of photovoltaic energy harvesting, where the Shockley-Quezier limit for our sun tells you that it's around 1.3 to 1.4 electron volts, which is where their band gaps lie. This is where the TMDCs lie. If you compare it to all the other semiconductors, including ones that are used for photovoltaic applications, you see that their absorption coefficient is actually larger than most other known semiconductors. And this actually got us first excited that, what if you could make photovoltaic devices out of these very thin exotonic semiconductors? Now, we did a lot of research on it. It's a fairly well-established idea now. But the other thing that we found in the process of making photovoltaics for them is we were looking at the optical constants, or both real and imaginary part of refractive index of these materials. Here, for example, is the N and K of bulk WS2. And what you end up seeing is that even for bulk WS2, you have the optical response is quite wiggly, which means it's dominated by excitons, as I was explaining to you in the previous slide. But the other interesting thing that you very quickly see is that the value of these refractive indices, okay, both real and imaginary part, is actually very, very high. Okay, so even when the absorption stops at around 700 nanometers or so, you look at the real part of refractive index, which is N, it is above 4. To give you a sense, people consider diamond as a high refractive index material and a diamond as an index of 2.2. We are talking about almost twice the size, the refractive index value that of diamond, which means that these materials are excellent for trapping light within them. Okay, so that raised very interesting possibilities, and we started thinking about how can you use these materials themselves to trap light within them without the need of other optical elements or optical cavities outside. And so this was the postulation that we started to look at, is if you had freestanding transition metal dichalcogenide layers, they would typically absorb just 10 to 15% of the light. But if you were to put them on a reflective metal substrate, such as gold and silver, allowing the light to bounce from the backside, by virtue of the high refractive index and high extinction coefficient, you could have destructive interference happen even in just a few nanometer thick material. And this destructive interference occurring due to bouncing back light and the other incoming ray of light would lead to nearly 100% absorption without the need of any external optical cavity. This is very important. Most of the time, people would need some kind of mirrors on both sides, okay, or some very complicated optical resonator structure to actually bounce light many times inside and trap it. Here, what we are speculating is that you don't need any of it. All you need is just one mirror and a material with very large optical constants, both refractive index and the extinction coefficient. So we set out to explore that. We figured out this is indeed true. It happens. We published a number of papers on it too. And so I don't want to go into all of those papers, but you can read some of this work earlier that we published. But what I want to get to is actually a more interesting fundamental physical phenomenon behind it, is that when you are able to trap light into this material itself without the need of external cavity, what happens to that light when it interacts with the exciton, or when it resonantly interacts with the exciton in the material? And so this is something that I started looking at, or we started looking at when I started at University of Pennsylvania. And I got some undergraduates to do some simulation studies first. So I told them, why don't you go and find out for me how would the reflectance spectrum of tungsten disulfide would look like on gold as you change the thickness, okay? So when you first look at it at larger thicknesses, you see a nice dip in reflectance that happens at the exciton energy, which is about 2 electron volts at around 620 nanometers or so. But what you see, which is quite interesting, is as you reduce the thickness, at a certain critical thickness, this exciton peak splits into two peaks. Okay, the splitting is actually very well visible in experiments too over here. Okay, and the splitting occurs. And if you look at the entire spectrum, then you see that there is another line, another mode over here. This another mode is basically crossing this exciton mode, and therefore, when these two modes cross, they form an avoided crossing structure, this cross-like structure over here, and then you see the splitting emerging over here. This is the classic signature of strong light-matter interactions or formation of exciton polaritons. You would call this an upper exciton polariton branch. You would call this as a lower exciton polariton branch. And this mode is typically what you would call as your cavity mode. Some people like to call it a Fabry-Perot cavity mode. I don't think it is necessarily Fabry-Perot because it's a lossy medium, right? So when you take the experimentally observed points then and overlay it on the simulation spectra, you see that they match up quite well. These circles are experimentally measured points, and this is observed really very, very well. You can also do very basic first principles calculations of two coupled mechanical oscillators And once again, you will find that these dashed lines actually fit quite well to what we are observing over here. So this was very neat, very interesting. At room temperature under ambient condition, we are seeing splitting between the exciton modes to form exciton polaritons of the order of 170 millielectron volts, much larger than the room temperature thermal energy. So we were like, well, can you see this even more? And the answer is yes, you can see it even more if you go to larger thicknesses and formed higher order cavity modes. So if you go to larger thicknesses, you will find even more larger splitting because the cavity modes become stronger and stronger within the material. So then we ask the other question, can you see it in other types of exotonic 2D semiconductors too? So we started with WS2 and we started looking at WSE2, and then we also looked at it in MOS2 and MOSE2. And in all of the cases, we were able to see this kind of exciton polariton splitting, not just on gold substrates, but even if you change it to other reflective substrates such as silver or aluminum, you can see the splitting emerge very well. So then the question was, does this happen for 3D semiconductors such as gallium arsenide or gallium nitride or gallium phosphide, which have similar band gaps as these TMDCs? The answer is no. We were not able to see this kind of splitting occur in these 3D materials. And the answer to this, or the reasoning behind this, is that you do want the optical dielectric function or the oscillator strength to be focused into the excitons. If you don't have the oscillator strength focused into the excitons, then this kind of strong light matter coupling is not going to happen. So therefore, having a strongly excitonic response in the material is quite important to observe this. So then the next step was, what happens if you then start patterning this material to start making the, some kind of photonic crystal out of this excitonic material? So naturally, we took our TMDC crystals and started etching the nanoresonators in them. And so this is how some of these nanoresonator structures look like. And so immediately what you do is that you break the symmetry along one polarization of the light where there is no change in the structure, versus along the other polarization of the light, which is TM polarization, you have changed the symmetry. And so now what you immediately see is that along one direction, you again see the exciton polariton coupling with no change in the spectrum, but along the other direction, you see that the spectrum has completely changed and these new peaks start appearing. These triangles and squares and crosses are experimentally taken points superimposed in the simulation spectrum. If you try to go and do simple electromagnetic wave simulations, you find out that now you are introducing plasmon modes that are confined at the interface between the excitonic material, which is WS2, and gold, which is the plasmonic medium over here. And so you can also see this very well in experiments, as you can see over here, very sharp, nearly 100% absorbing hybrid plasmon exciton modes that are appearing in the patterned system. And so you can derive the entire dispersion of the system by looking at, as a function of varying widths for a fixed period between the resonator, how does the dispersion spectrum look like? And you can see that as you start patterning this medium, you see first, second, third, and fourth order plasmon mode emerging as you pattern the TMDC layer on top of this substrate. So this was actually quite interesting, and we figured out a whole new modality of coupling, strongly coupling light and matter excitations. The matter excitations being excitons and plasmons, and light being photons. But then the key question that we wanted to ask ourselves is that if you talk about all of our structures, they are based on WS2 with much larger thicknesses. This is a few tens of nanometers. What would be interesting to do, and so we published all these results in this paper, which you can look at, but what would be interesting to do is what happens when you actually go to monolayer limit. Now, why is monolayer so important and so interesting? And the reason being that monolayers are direct bandgap semiconductors as opposed to multi-layers, which are indirect bandgap. Second, monolayers are sub 1 nanometer in thickness. They are just 3 layers of atoms. Okay, so then that raises an interesting question, which is, if you have just 3 layers of atoms, how much light can you trap in them? And so to investigate that, we postulated a few techniques by which you can trap a lot of light into the monolayers. And we postulated this several years ago. Some people realized some of these structures, but none of them were perfect. So then I told my students, once again, that why don't you start simulating some structure where optically the material looks like multi-layer, but electronically the material behaves like a monolayer, okay? And so they came up with this structure where you have many monolayers, but they are separated by thick enough layers. Here by thick, I mean about 3 nanometers or so, such that there is no overlap in the wave function between the two layers. Okay, so they retain a monolayer character, yet they behave like multi-layer to the incoming light. And so they came up with this artificial alternating exotonic semiconductor and a dielectric insulator type structure. We call it exotonic metamaterial, right? And they told me that the optimal thickness for the spacer layer in between them, this could be hexagonal boron nitride or ALD grown aluminum oxide, is about 3 nanometers. And for even these number of repeating unit cells that you have in the structure, even for like 5 or 6 repeating unit cells, you can get nearly 100% absorption at the exciton. So I'm like, this is quite exciting and quite interesting. We should go and try to make this structure. So I told them to go in the lab and make this structure. So they went and started exfoliating these crystals and started stacking them one on top of the other, boron nitride and molybdenum disulfide. And they came back in 2 weeks and told me, Professor, we cannot do this. This is too hard. By stacking multiple times, we are left with an overlapping area that is so small that you cannot even do any reliable optical measurement. So at that point, I was like, okay, fine. We need to have some mercy on the students and find a different way of doing this. And so that's where we went to large area CVD grown material. So this is actually, you can make it over wafer scales now. We work with our collaborators, Joan Redwing at Penn State, as well as Extron, who can grow these at large areas. We can also grow some of them over very large areas. And companies like Extron can actually grow over a full 8-inch wafers. So these are now real materials that can be scaled up to very large areas and therefore very promising for applications. And so then we took some of these materials, cut them, cut up the wafers into smaller 1 by 1 centimeter samples, and started artificially stacking these monolayers or monolayer of exotonic semiconductors to make these super lattice type structures. And you can see very nicely over here, as I change the number of n or increase the number of n, by the time you reach n equals to 8, you can see nearly dark green to black looking film, which tells you that it's absorbing a lot of light. And even in the absorption spectrum, you can see that by the time you reach n equals to 5 layers, you are absorbing more than 90% of light at the exciton. Even in the TEM, when you cut these samples and visualize them, you can see very nice artificially stacked multi-quantum well structure with monolayers of tungsten and sulfur showing up really quite well. And in between them, this hexagonal boron nitride layers also showing up very, very well. So the interesting thing about this kind of multi-quantum well or artificially assembled multi-quantum well structure is that it can also self-trap the light. So when you try to measure its dispersion relation or its simple optical properties as a function of angle, you realize that beyond a certain amount of angle, the light that is coming into this multi-layer structure, it bounces around and forms a waveguide mode. And this waveguide mode then couples strongly with the excitons in the system to again form exciton polaritons. And if you are able to see these exciton polaritons quite well in both simulations as well as experiments, and the splitting is very, very neat. So we were quite excited by this result. And the next step over here is actually take it and tune the exciton polaritons to actually make optical modulators or look for exciton polariton type lasing. And so this work was published also earlier this year. And so feel free to take a look at it. And the next system we try to look at now is naturally occurring naturally occurring superlattice structures. So here we artificially made these kind of layered structure, but there are certain types of crystals that occur in nature. And these are the halide perovskite crystals, where you have inorganic and organic layers that are alternating. And even these materials are strongly excitonic in nature. So we were like, well, they should be able to support exciton polaritons just by themselves without the need of any artificial layering. And so the problem is to make these structures in high phase purity. You cannot make these crystals in very high phase purity. But by collaborating with our good friend Aditya Mohite at Rice University, they were able to make these crystals, which are highly phase pure. Okay, so here is, for example, n equals to 1, 2, 3, 4. That signifies the number of lead iodide layers, the number of unit cells of lead iodide that are stacked together. And so they were able to make these very highly phase pure crystals as verified by XRD. And then we were able to measure their optical dielectric function, which showed very nice sequence of changing quantum confinement as you change the number of layers with very strong excitonic properties. Okay. In fact, the excitonic properties of some of these halide perovskites is actually very, very strong, comparable to monolayer WS2, and the electric loss tangent is comparable to some of the laser dye molecules. And so therefore, we are of the opinion that there could be very interesting materials for lasing devices, because from the dye molecules you can already make pretty good lasers. And so we actually published this one too, to make it easy for the community to use these optical dielectric functions and design their own devices. And so it was very natural for us to again trap light into these materials by putting them on reflective gold or silver substrates. So we were able to do that, and we were able to see very large absorption for sub 20 nanometer thick layers, approaching 100%. But when you go to thicker layers, we started seeing the splitting, the Acetone Polarity splitting again. So this was quite exciting for us. And so we looked at this in much more detail, and we were able to see that as a function of thickness, you once again get this nice anti-crossing curves. But more importantly, in these materials, because they are naturally direct band gap, because the separation between individual naturally occurring quantum wells is quite large, you can get very large amount of luminescence efficiency. So light can come out very well of this material. So even at room temperature under ambient conditions, we are able to see polariton emission. So upper polariton, higher order mode emission, as well as lower polariton emission. So this was actually quite nice and exciting. And we are now trying to figure out if we can see polariton lasing from them. I want to skip this slide because this is just going into the details of how the coupling strength increases as a function of the quantum confinement of the exciton. But there is nothing more important than that, and it matches actually quite well with theory. And the next step is to go for polariton lasing, which is actually quite hard to do. So the last thing I want to touch upon, and I think I have a little bit of time still, the last thing I want to touch upon is a very new direction in photonics and optical materials that we are taking, is looking at magnetic semiconductors. Okay, so magnetic semiconductors are a difficult species because most magnetic materials occur as metallic in nature. We know of iron, we know of nickel, we know of chromium. All of these are also metals. So to find semiconducting materials that are also magnetic is actually quite difficult. But recently, in the world of two-dimensional materials, people have found many magnetic materials, and some of them are semiconducting. The ones that I'm focusing on, they are actually anti-ferromagnetic semiconductors. Now, why do I say anti-ferromagnetic? Because they do have magnetic order, but they have alternating spins. Okay, so the two types of compounds that I'm talking about are iron phosphorus sulfide and manganese phosphorus sulfide. Okay, in both of these compounds, you have iron atoms or manganese atoms that are magnetic, right? And they are arranged into this hexagonal pattern. And in the case of iron phosphorus sulfide, the iron atoms have spins aligned this way. So if all of these red are spin up, then all of the blue are spin down. Similarly, in manganese phosphorus sulfide, if all the blue are spin up and all the red are spin down. So there are different types of antiferromagnets. Okay, so people have found all classes of compounds in this, iron, nickel, manganese, or even in some cases, chromium, phosphorus sulfide, and selenide. They are all antiferromagnetic in nature. And they have found that their Curie temperatures for magnetization are of the near liquid nitrogen, or even below the above liquid nitrogen temperatures. They are quite good. And so depending on how the spins crystallize in these materials, you can have a zigzag type antiferromagnet, or you can have a Neal type antiferromagnet. And depending on whether it's zigzag type or Neal type, you have very different optical properties. For example, in the zigzag type magnets, you can have a very large optical linear dichroism, or LD, and I'll explain what that is. Whereas if it is Neal type, you don't have LD, but instead, because of this type of alternating spins over here, you can generate a large amount of second harmonic generation over here. Whereas in this in the zigzag type, you don't have much the second harmonic generation. So this was again very interesting for us, and we started looking at it from the perspective of, can you use magnetic properties of the material to change the optical properties? Because this is something quite new. It has not been done in photonics before. So we started looking at it very carefully, and my student found that as you cool down these materials and make it go through the magnetic transition temperature, which is about 118 Kelvin for iron phosphorus sulfide, we see that the linear dichroism in this material. Linear dichroism is a difference in the polarization response of light shining on this material. So if your light can polarize this way versus this way, the electric field polarization, the difference in the two leads to linear dichroism, we see that it approaches nearly 100%. This was actually quite surprising to us. We haven't seen materials before that show this large amount of linear dichroism. So we looked at it and investigated it further. First, I didn't believe my student. I asked her to go repeat the experiment several times, and every time she came back and said it's the same result. And so we started looking at it more carefully. And what we saw that as a function of changing polarization angle, indeed at low temperatures, you're seeing that the reflectance spectrum is shifting quite a bit, right? And so from that, if you then extract the polarization plot, the polar plot, and plot the linear dichroism, which is nothing but given by this very simple formula, reflectivity along one direction versus perpendicular direction. They should just be separated by 90 degrees. Subtraction and addition of the two sides, and you get the linear dichroism percentage. And we were able to reproducibly see that the percentage can approach nearly 100%. This was quite exciting. And so we started looking at it in even more detail, that how does this vary as a function of thickness? And we were further able to confirm that as a function of thickness, you can actually tune this linear dichroism, and you can tune it spectrally. You can take it all the way from blue part of the spectrum to the red part of the spectrum and near infrared. And by applying standard transfer matrix model, you can also get a very nice simulated spectra for the same, showing that indeed what we are seeing is coming from standard optical cavity effects. You can extend it further in another direction by changing the cavity medium altogether, not only by changing the cavity medium of the material itself, but also by changing the cavity medium around it. So that means the substrate that is being put on. And so you can now generate these nice design plots of looking at the thickness of the magnetic material or the thickness of the substrate it is on that forms the cavity. And we have investigated it for several different thicknesses, as you can see from the star and square and triangular points. And all of these experimentally measured points actually fall quite well on the simulation. And so this is also something that we published recently. It just came out a couple of months ago. And the main message over here is that now you have a magnetic knob. You have a magnetic knob to tune the optical properties. And the next steps that we are going to take, and we have shown some preliminary data in this paper, is that by applying magnetic field, you can change the magnetic orientation of the spin chains. And that can lead to dynamic tuning of linear dichroism in these materials as a function of applied external magnetic field. So in our opinion, this opens a whole new area of what I like to call it as magnetophotonics, where use of external magnetic fields and internal spin order in materials, you can control the flow of light within a medium, opening a whole new direction for light matter coupling and tunable interactions. So with that, I think I'm running out of time. So I'm going to stop and summarize over here. And I would like to mention that understanding fundamental light matter interactions is quite interesting and important in low dimensional semiconductor. And I think 2D semiconductors as well as 1D carbon nanotubes have some very important and key attributes that make them very interesting avenues for light matter coupling phenomena. They concurrently have high index. They are very easy to integrate and fabricate. They all support excitons, or most of them do, and their indexes are tunable, and they have high nonlinearity. It's very hard to get all of these properties together in one class of materials, and therefore I think they are quite interesting. But the challenge remains is actually making practical technology out of them, and this is where growth and manufacturing of these materials, both monolayer as well as larger thicknesses, over wafer scales, and assembling them into repeating units like we have shown is actually quite important. And this is something that I emphasize the entire community to focus on. And finally, if you want to think about new physics, then looking at active tuning of optical properties using magnetic field or strain is also another very interesting direction where you can use these novel two-dimensional materials and opens up a whole new avenue for nanophotonics. So with that, I would like to thank a large number of people, but the funding agencies that support us, but most importantly, the students and postdocs. These are the real heroes. They are the ones who make all this possible that I can present to all of you. And none of this work happens without a very strong set of collaborators all over the world, but most prominently, Joan Redwing at Penn State, Arthur Davoyan at UCLA, my colleagues Zahra Fakhra and Liang Wu, and as well as our great collaborators AFRL and Rice University. And with that, I'd like to end and thank all the students again for their work. I would like to note that all of those papers that we have published have happened after the first wave of lockdowns. And so really the credit goes to all the students who made all this possible, that each and every one of this paper was published after March 2020, right? So it's really all of their effort, and I'm only the fortunate or unfortunate phase who gets to present their work. And the publications in blue are the ones that I highlighted today. And I'm happy to take any questions from all of you.
Thank you very much.
I'm sorry.
Go ahead. Go ahead.
Yeah, so thank you very much for both of you. And then I'm a little bit getting jealous with this last page. So this is too productive. Okay, congratulations. So we are moving towards the on-site, sorry about that, the panel discussion for half an hour, for the next half an hour. So we've got some questions from the audience. So Martin will speak the questions for you.
All right, thank you, Ms. So we have two questions. The first one is from Jiang and is for Professor Haiding. Wonderful works, thanks. And the question is, how do you control the uniformity of the nanowires for PD? And will the aspect ratio and dimension of the nanowire affect the performance?
Okay, great. Thanks, Martin, and thanks, John, for your nice question. And actually, this is very critical for nanowires, especially how we are able to control the uniformity of the nanowires. And for those, what I presented is a naturally random grow nanowires. The uniformity can be controlled by the nucleation stage, and it's grown by the molecular beam epitaxy. So it's very advanced growth tools. Unlike those CVD grow nanowires, it's like nanowires can grow randomly, like form a net. But you can see that our nanowires are vertically grow nucleated on the silicon substrate and can grow vertically. And the uniformity in terms of the height and the dimensions can be controlled relatively well, unlike those CVD grow nanowires. But if you really wanted to indeed control the uniformity of nanowire into the very exact same of the height, same of the diameter, you may need a selective area growth mode of the nanowires rather than the way that we grow randomly, uniformly nucleated on the silicon substrate. So it depends on the growth condition, growth substrate, and the growth techniques. So it's a very critical question, but it depends on the what you are pursuing for and whether you want exactly the same or you just want to, like the way we presented, almost more or less the same, right? The height and the dimension. So will the aspect ratio and dimension of nanowire affect the performance? Definitely. This is very important, and especially what we learned that even we on the same wafer, when we change the growth temperatures, the density of nanowire will change from the middle of the wafer across the wafer to the edge. So basically, the uniformity, the aspect ratio, the height of nanowire, the dimension of nanowire will be slightly changed, even from the center of the wafer to the edge of the wafer. So it will affect the light absorption. It will affect the light, the photogenic carriers extraction and migration. So this definitely will affect the performance, and this is an important topic in the nanowire community, how we are able to control the aspect ratio and the dimension of the nanowires, to understand them well and to correlate with the performance of the nanowire-based LED, nanowire-based photodetector, nanowire-based of the lasers. So they are very strongly correlated. Yeah, I hope I can I explained clearly. Yeah.
Thank you very much for that very detailed explanation. The second question is for Professor Deep. Very good work. And the question is, could you explain what is the law of interfaces in the observed plasmonic responses? And the person asked about slide 10. And then also, can you describe the role of sub-nano surface roughness of the substrate on your data?
Yeah, so thank you for this question. This is actually quite a careful observation and a good question. You are right that you need to have very flat surfaces and interfaces between the 2D chalcogenide and the gold in order to get these very sharp and reproducible plasmonic responses. The reason being, if the gold itself is rough, or if the TMD itself is rough, then of course it can lead to other type of surface plasmon resonances because of the change in the dielectric medium between air and the gold. And so to ensure that we get this very reproducible, very nice responses, we go after a technique known as template strip gold. Okay, this was a technique which Martin may know very well, but was developed part of it was developed in George Whiteside's group at a time. Is you take a silicon wafer or any other really flat wafer, you evaporate gold or any metal on top of it, preferably a noble metal, and then you put some glue on the top of the gold or a metal, and then you take another piece of silicon wafer or a glass slide and just stick it. Okay, so now that you have stuck another piece of a glass slide or wafer on top of the gold film, you can then take your razor blade and peel it off. So when you peel off this gold film, you expose the bottom surface that was sticking to the silicon wafer, and now you have flipped it over to make it the top surface. This means that the gold film that is now exposed at the top has the same surface roughness as that of a silicon wafer. So in our template strip gold films, the RMS surface roughness that we measure via AFM is less than 0.1 nanometer, which means it is so smooth that you won't have any spurious surface plasmon resonances coming from the asperities or the roughness intrinsic to the gold. And so therefore all those resonances are eliminated, and we are able to see very reproducible responses when you make a 2D van der Waals interface with this template strip gold. I hope that answers your question.
Thank you. I hope the audience gets the answer. That's very good, and glad to hear that you're using template stripping. We like that method. Thank you. Miso?
Okay, so we just wrapped up the Q&As, but we can continue more questions and answer time. And then, so if Martin has any questions for you too, the academic questions first, like about the presentation.
Oh, sure. I'm going to start with Deep. Very, very good work. Very interesting. And actually, as you answered in the previous question from the audience, something came to mind. When you have multi-layer of your 2D materials, the energy difference between the substrate and your 2D material is going to could affect the band structure at the interface, because there's a resultant dipole, right? Gold has a Fermi level somewhere, is it about 5 or something like that? Which is very different from the 2D material. So the first layer that sits on gold, it will experience a very strong interfacial dipole. And then as you put more layers, that effect is significantly perturbed in the following layers. Do you see any form of like interface or gap-induced band structures that affect your response?
Yeah, so again, very careful observation and very good question. So you are right. The first layers that will sit on the gold or silver or any other metal, they would have a giant amount of charge transfer from the metal into the semiconductor. In fact, it leads to degenerate doping of the semiconductor to the point that the entire exciton can get extinguished. Okay.
Oh.
And this is something that we have studied separately in a separate context, and there are a whole series of papers on that too. But the context in which we have studied this is actually making electrical contacts to 2D semiconductors. This interfacial charge transfer is really important to that. Now, in the optical regime where we are investigating many of these materials, these effects vanish by the time you reach the 3rd or 4th atomic layer. Which means if your sample is more than about 2 nanometers in thickness, these effects are going to more or less completely vanish. And so in most of the work that I showed you, especially the ones where I was changing the WS2 thickness, the critical thickness at which the Acetone Polarity coupling occurs, it's about 10 to 15 nanometers. So by that thickness, the effects have almost completely vanished, right? Yeah. But if I were to do this with monolayers, it would be a very different ball game. And I would have to devise a careful way of introducing a thin spacer layer between the monolayer and the gold to avoid this charge transfer.
But if I can have a follow-up, sorry, Miso, quick follow-up on that. It's very exciting what you're doing with magnetophotonics. To be able to couple bosons with fermions is really, really exciting, because you're getting into a territory where you can start perturbing energy density that gets to transfer to a material. And when you showed that, that's when the interfaces came screaming at me. And I was wondering, could you actually use the dipole, any interfacial dipole, as a way to gate the optical response, the same way you're using magnetic moments? And is there an opportunity? I don't know whether you have an answer. This is a hypothetical discussion now, but it will be very interesting to see how we can use those interfacial dipole and asymmetry in band structures to start controlling light responses, because those are dimensionally restricted. Fermions, because of Fermi-heap and Fermi-holes, you cannot concentrate them. But bosons, you can concentrate them. You can concentrate as much light as you want. And how much do you need of the fermions to significantly perturb or control these super concentrated bosons? It's a very interesting question. I hope you pursue that and give us an answer.
So it's an interesting question. I have, I have plans to pursue it, though I will say that it will take some time to pursue it. But one of the interesting ideas that people have tried to explore this is, now that you have these interfaces between magnetic materials and magnetic semiconductors and metals, right? What happens when using light or using electric field, you can switch magnetization, and how does it affect in terms of a conversion of this magnetic moment into or the spin to charge coupling? Does that lead to generation of some kind of photons, right? So this boson fermion interaction that we talk about, and there is a whole community of people in terahertz photonics that is trying to look at that as a function of magnetic switching, can you generate short terahertz pulses at these interfaces, right? Now those require much more elaborate experiment, especially because terahertz generation requires also a larger area of the sample, just because terahertz light has a much longer wavelength. And so I am not actively working on it, but I have plans on it. I have written proposals in that regard. And then there are other collaborators, some at University of Delaware, not too far from where I am, who are looking at this actively. So it's a very exciting future prospect that you brought up. And I'm sure if not my group, somebody else will pursue it and come up with very exciting developments in the future.
I'll be very curious. Miso, do you have a question, or can I go to Haiding?
Yes. Yeah, you can keep forever.
I don't want to hold the pen. Go ahead. Go ahead. It's your turn.
So by the way, Deep and Haiding, you can ask questions to each other as well. So all of us are allowed to ask questions. So just prepare. So back to Haiding. I love your work about the miscut sapphire substrate. So I love the idea, especially. But I was wondering, so when you miscut the sapphire, there should be some tolerance, the fabrication tolerance probably, because every time you cut the sapphire along the texture, but it doesn't come out like ideally, right, in terms of fabrication. So how do you deal with it? And was there any problem like that?
Okay, great. Thanks for your question, Miso. And I think it's very critical and preparation initially for the nucleation stage and how you treat the sapphire substrate. Normally we will do annealing. So although we have steps, like one step, but if you anneal it as substrate before you do the growth, the step edge will become more kind of smooth in terms of the very sharp steps if you anneal it at high temperature. So this will facilitate the atoms like being moved around when they arrive on the top and then move around. So this will help us to make it more soft rather than extremely sharp steps when you cut the sapphire, because mechanically polishing definitely will create those kind of steps, right? It will not help nucleation. And so what we learned that after annealing, you will be able to smooth the surface while keep the terrace or bunches step by step, but on the edges very smooth. So this will help us to grow high quality films. And but if you have very super large miscut, ours we found that it's 4-degree miscut. Maybe if you pay attention to, when I present, we use 4 miscut. This is an optimized miscut. Rather than 1 degree, it's like a no miscut, right? It's the same as the original one. If you have miscut like 10 degree, this is extremely sharp. You will not be able to achieve any very smooth film anymore. So you have to have a balance. And once you have the balance, and you will be able to grow quality films. Yeah.
Okay, very nice. You have a secret recipe. So
Yeah.
okay, by the way, you managed for 40 minutes very nicely. So you didn't have to worry about your time.
Yeah, I speed up a little bit. You see, when I talk a little bit more about the detail about LEDs, I found that there's only 5 minutes left for my photo debate.
You were so excited.
Immediately ramp up. So, okay. Great. Okay, by the way, so you mentioned that I'm able to ask questions, right? So I'm very curious about it, and very exciting to see the Deep present such a nice presentation, especially the Nature Photonics paper. And because I'm working on the nitride, right? You know that when I was looking into, I'm indeed looking into the low dimension of the nitride. And I was just shooting your figures, sent to my student. I said, please look at these 2 papers published in Nature Nanotechnology and Nature Photonics. How like Professor Deep can generate such beautiful stack of the multi-layers with super different. Okay, it's not like gallium nitride, aluminum nitride. It's gallium nitride, it's boron nitride with something extremely different materials. I was hoping our student can achieve this, because when I put 2 papers, you see, I see when I put 2 papers together, they are pulsed or they are absorbed or they are connected together. When you put so thin film together, I was worried about you're going to roll up a lot of like those films. It's not flat, it will roll up or something like this. And my question, how you are able to avoid this, and what do you explain to me about the gold? It's very exciting to see that your film surface is like less than 0.1 nanometer AFM measurement, which this number is very, even like when I grow my material by MOCVD or MBE, I cannot get 0.01 nanometer scale like roughness, surface roughness. How you are able to achieve that? And can you explain more about how you are able to stack? The second question is, maybe you go first with this one question.
Yeah. So I think the fundamental difference lies in the fact that these are van der Waals materials. So the multi-layer stack that you saw, it's between MOS2 or WS2 and hexagonal boron nitride. So both are hexagonal materials, but their A-axis lattice constants are quite different.
Yeah.
And but because they are van der Waals, they can exist as freestanding monolayers without bonding with the above layer and causing it to roll or scroll or things like that. Those are normally the problems that you have with 3D bonded materials, right? So when the materials are van der Waals or 2D, you can take 2 arbitrary layers with a different crystal structure, completely different lattice constants, put them on top of one another, and they will just stay. And this is the fundamental difference between 3D bonded epitaxial materials versus 2D bonded van der Waals materials. And that is why the whole community is so excited, because in many cases now, you don't need epitaxy. You don't need epitaxial matching. You can mismatch materials as you want. So that is why the part of the excitement is there over there. So what we do is we take one layer, like hexagonal boron nitride, we stack MOS2 on top of it, and that's it. It's like sticking the sticky tapes on one on top of the other, right? That's all. You just keep stacking as much as you want, and you can build these layers.
Okay.
And then with regards to the question about very smooth gold, I think it's as the name suggests, it's template stripping technique, or there is a template involved. What is the template here? The template is the surface of the silicon wafer. Okay. So if your silicon wafer surface roughness is 0.1 nanometer RMS, which is true, right? If you buy silicon wafer from the market, they have this good surface roughness. Then whatever film is going on top of it, the bottom surface of that film and the silicon is also going to have the same roughness, right? Because the silicon has transferred its surface roughness to the bottom surface of the gold film. All I'm doing is I'm peeling off this gold film now. If I'm peeling it off, I'm exposing the bottom surface of the gold film, which had the same roughness as the silicon. So therefore, the roughness is so smooth.
Okay, great. I have one more question. Sorry, Martin and Misu. And very interesting on stacking different materials. So I was wondering, have you thought about, rather than using the, for example, MOS2 with boron nitride, because I grow a lot of gallium nitride and aluminum nitride quantum wells, right? So what do you expect? Do you expect to see something similar, fundamental, whatever plasmonics or cavities, whatever you see? Is that possible to see that in our gallium nitride? If so, then tomorrow I will grow and let's see what's going to happen.
Yeah, so in principle, yes, it's possible. The dimensions may not be the same. What you need to figure out, to be very precise about this, is what is the oscillator strength of excitons in your gallium nitride quantum wells? Because that is one fundamental parameter that will dictate the design of the optical structure. Okay.
Exactly.
So once you figure that out, we can collaborate on this. You can ask me, and I can tell you how what parameter to vary to see what structure. Yeah. So I think that is something important to find out. What we have been trying to do is actually grow. I mean, we are working on nitrides too, but we're looking at boron nitride, and we are looking at scandium doped aluminum nitride. It's another exotic nitride material. It's ferroelectric in nature. We are trying to grow some of these 3D nitrides on 2D materials and then trying to peel them off. So we are trying to separate very thin layers of 3D grown materials by growing them on 2D and then peeling them off, so that now you relax this constraint of stacking arbitrarily, even for 3D materials. So that is the next phase of research that we want to go to in this. And so it will be quite exciting, because these optoelectronic nitrides that you presented, as you said, there's a huge market opportunity there.
Great. Thanks for sharing. Yeah, this is very exciting. And you mentioned that we can peel those 3D and put them together, right? Yeah.
Yeah.
Okay. Thanks. Hope to collaborate in the future. Yeah.
Sure. Yeah. More than happy.
Yeah.
Yeah, I'm very happy to see you to discuss your future plan here. So, okay, so let me ask some of the questions not quite related to your presentation today, but like related to your career, because you guys have gone through like a very successful research career for now, and then we want to find out your secrets, as Alice said. So, who wants to go first? So, I would like to ask if there are any advices for your graduate students or undergrad students all over the world out there who are listening to your panel discussion right now. So probably Deep.
I can
first.
start if you want.
Yes.
Yeah. So thanks for raising that up. I think the advice I try to give undergrads and graduates both is that in your time in school is very unique time in your life, especially if you are a PhD student. I don't think you're going to get that kind of a time again in your life, where you have 4 to 5 years that you are free to explore. And you should take this opportunity to explore and develop yourself intellectually and creatively, right? And it's important to have a supporting advisor too in that regard. And I try to do that with my students. I just tell them that go learn about many different things, read a lot of papers, read papers from many different areas. And once you build a critical base of knowledge by reading from many different areas and many different fields, then you will start developing this ability, again, with help of your advisor or by looking at other people, how to connect pieces of knowledge from different areas of research. And that leads to actual research breakthroughs. This is very, very important, because if you look at the body of research literature these days, it's huge. It's absolutely humongous. So it's very difficult for younger people or younger generation scientists like you all to find out where are the important problems, or what connecting what to what will lead to the next breakthrough. So that is why having a broad knowledge in terms of reading and utilizing this time as a graduate student or undergraduate to read about many different areas is extremely important. The other piece of advice that I will give is that it is very reasonable or very common for experiments or projects to not work. Okay. My own PhD research, until my third year, I had perfectly 0 papers. My PhD advisor had probably abandoned all his hopes that I would be having a successful PhD. But in my 4th and 5th year, I published 5 papers each, and everything was fine later on, right? So it's very okay for things to not work. The important thing is to be creative, be brave, and explore, and in the process, learn a lot, because it takes a while for important and difficult research to work. But once it works, you would have accumulated so much of this extra surrounding knowledge on what makes it work and what does not make it work, that you would absolutely capitalize and be the leader in the field. So never get disheartened when things don't work. You have to keep trying, be creative, and do different things. And in the process, it's most important to learn.
I was trying to memorize everything because I want to tell my students on Monday morning. So
You can pass the video to the students.
yeah. Okay, thank you so much. So Haiding, would you wanna?
Thanks for the question, and I appreciate the deep suggestions. And the only thing I wanted to add on upon what Deep has mentioned, that yes, you have to find, you have to brave, you have to be self-motivated, you have to be consistent and persistent, rather than just, oh, I find this experiment failed and disappointed and I don't want to work on anymore. But unlike the way it should be, like the way Deep has mentioned, is very to be creative and persistent. And another thing is, when for the graduate and young student, is my suggestion is you always have to find a very energetic and supportive advisor, right? Because that's very critical. Is some of senior mentors, although they are very reputable and very highly recognized in the community, but as a young student, you have no experience about research. You must have someone can teach you in hand by hand, and even how to wash your wafers, right? It's very critical, because when I learned everything by myself, and I feel like my advisor was so senior, and I'm afraid to bother him, said, okay, can we go into the clean room and let's work on some of the wafers? And as a result, in the very beginning, I feel like a very slowly progress. But I'm fortunate to have a senior member who can teach you hands by hand. And also later on, when I go to postdoc or go to another school for after my PhD, my collaborators, they are all very young and energetic, and they have very experienced techniques to teach you. And so for PhD or for graduate school, do not always go with schools. You always go with advisors. That's what Deep mentioned when we chat, when we were online in the very beginning, is why all the MIT students come to me, right? Previously, they always go to MIT and Harvard. Why go to Deep as a young scientist? And it's because people will see that for those young advisors, and also it's not young, but also this young scientist has to be very productive, right? So as a result, when you join such group, you will be embraced by your advisors, by the team members. Everyone is supportive, because we build from scratch, and everything we teach you how to do it. then you will be very productive. Maybe in the very beginning you are not productive, but later on when you accumulate those knowledge and techniques taught by those senior members and young advisors, you will be very powerful and to connect all those techniques together and make creative work. So that's what I learned is from that my colleagues and my friends who were as smart as hardworking as me, but they go to academia. They don't go to academia, they go to industry because their publication is not that high in terms of the when they graduate and when they pursue their dreams. And they found, oh, I wanted to be a professor and I wanted to be a faculty, but eventually because of publication, they cannot go and they have to go to the industry. But if your goal is to pursue academia, it's better for you to find a balance that the group is very energetic and very productive, and the PI or the faculty members or the colleagues and the senior members are all very like hardworking and very creative groups, rather than you find you need to go to a very good school. No, for PhD and for grad school, no, that's not our first policy, our first priority, right? So that's what I want to add on. And then the last one is, the second point is you have to be extremely hardworking, because you see, and in 10 years ago, people maybe find a very good faculty position in MIT or UPenn with a list of papers. But now, if you go to MIT, Harvard, or maybe go to another small schools for interview as a faculty, everyone has a long list of publications. You must be extremely competitive in terms of your peers when you look for jobs. So you have to be extremely hardworking and creative and learn from your peers. And it's better for you also go into a multidisciplinary group. And this will help you to build up knowledge that nobody can teach you, and you will learn from your colleagues, you will learn from your classmates, and you will learn from the peers in the same group. That's why what I recruit when I recruit my students into my group, every year maybe I will recruit maybe 3 or 4 students. I will choose everyone from different backgrounds: material science, optics, even chemistry, physics, and electrical engineering. So in order to build them and put them together, and then, oh, the chemistry will happen. Okay, so that's what I share with my students as well. I hope to share with you guys is like, in order to be creative, you need to have not only on the very strong knowledge in the same subject, but also on to have new people coming in with different background and to build knowledge each other together and to find some new topics. Yeah.
Miso, can I jump very quickly into that?
Yes.
Actually, Haiding, you've hit something very, very important, and that is something that a lot of students don't pay attention to. And that is, number one, a student is not an expert. As a student, a postdoc, you are not an expert. Your job is not to produce perfect results. Your job is to ask questions. Actually, there is a very strong philosophy that a good student is not the one who gives the correct answer, but is the student who knows how to ask the right question. As a student, train yourself to question everything. Because as a student, by definition, you are seeking knowledge. You are a seeker. You're not an expert. And that ability to ask questions starts before you join a group. Haiding has hit on something very important. If you put yourself in a resource-poor environment and ride on reputation, ride on finding a shortcut to get your career, you will struggle. Look for a situation where if you're a seeker, you're seeking cognitive growth, look for cognitive diversity. When Haiding was talking about pulling people from different disciplines, those kind of teams that are cognitively diverse actually outperform the smartest people. There's a 16-year study going on at Harvard Business School, and the results are always the same. Do not put the smartest people in the same room. Put people from different backgrounds. Now, the problem with that is you will not agree with everybody because everybody is smart in their area. Everybody sees things different way. But by the time you're done in your studies and you figure out how to address people from different disciplines, you are going to be very successful. George Whiteside's group, Bob Langer's group, DeSimone's group, Stanford, all Zen and Bao's group, I can run down through all those groups. And you look at them, you will see that people come from all disciplines. As a student, if you specialize in asking questions, then you realize two things. There are resources that you can control. There are resources you cannot control. One of those resources is time. Time is one resource that you are guaranteed to lose. And there's nothing you can do about it, right? Question is, are you going to be transformed by the time you lose that resource? Or are you going to be moving backwards? A second law of thermodynamics working in terms of your cognitive growth or not, right? Do the thermodynamic calculation and see whether you're moving in the right direction. Entropically, if you're not diversifying the knowledge base you have, what Deepak was talking about in terms of broadening the knowledge base you have, you can get it through papers, you can get it through joining a group that is very, very diverse. So because you know you're losing time, maximize your entropy. If you maximize entropy, second law always works. You're going to end up fine. The second thing is there are resources you can control, people. Find people who will be around you that will help you maximize your entropy. Be challenged, be told things that you don't know. Find somebody in a discipline that will tell you something that you have no idea about. And never assume any discipline is not relevant to you. Well, if you're in photonics, you say, oh my goodness, what can I do with a biologist? Well, biology figured photoluminescence before we did. Biology figured optics before we did, right? You think, oh, you know, I'm in electronic devices, so how can biology help me? Well, photosynthesis drives all of us. It feeds us, right? That's molecular electronics. It's more complicated than the devices we can make. And I think no matter what discipline you think about, you can always grow in it. So I would say those are the 4 points. Resources, look for cognitive diversity, question all the time. You're going to lose time, it's guaranteed, but figure out what you're going to do as you lose it and maximize your entropy, not just by reading, but also putting people around you who are going to maximize how much change occurs in your thinking. That's what I tell my student.
Oh, yeah, I'm actually echoing the same thing every day to my students too. So I will repeat the same sentences again on Monday morning. So thank you, everybody. You did a great job. And then I wish we could continue like forever, like about discussing this, what important aspects we have to emphasize. But sadly, we are running out of time, so I have to move on. So let me briefly deliver the certificate virtually now, but Alice will give it to you later. So you guys did a great job today, and in December, you're so well deserved to get this award, and we are so proud of you. So this is the certificate of a Young Scientist Award for Professor Deep Jariwala here. And the next page, yes, Professor Haiding son here. And thank you so much. And then I hope that we can work together like forever with this ICANX platform talk.
Thank you very much.
Okay, thank you so much. So let me briefly preview the next week's talk. So the next week, we're going to have Professor Min Kyu from Westlake University, and with this amazing moderator and panelists again, and ex-challenger, Julia. So we are going to talk about he's going to talk about photon-based and electron-based nanofabrication technologies. And Martin, would you want to take over from here?
Thank you. Yeah, so the other thing we wanted to announce is since we have the Young Scientist Awardees from last year, the next group is already up and being recruited for 2022. And so the committee chairs are Paul and Alice, and the committee will be much wider than last year. We have a lot of people helping us look into the applicants. And we are looking for independent young scientists. If you obtained your PhD, after 1st January 2012, please do apply. What we need from you is one PDF package from applicants, your CV, include a photo and group website, your scientific contribution, short essay, outlook and research plan, and then maximum 5 representative publications or patents, and 2 recommenders. We will get letters directly from those recommenders. So please ask them to send their recommendation letter directly to us. Send all information to info@icanx.com by September 18th. Please do that, and the steps will be as follows. We'll review all the materials by October 28th, and then the finalists will be announced on that Friday. Then step 2, the finalists will give presentation, followed by Q&A, and this will be on December 2nd and December 9th. The award ceremony will be on December 16th during the ICANX Summit, and this summit is going to be in Senegal, Dakar, Senegal, during the African AMRS, and then there will be a prize of $1,000, and then all the winners will be invited to give talks in 2023. We are right now sponsored by SES Nano and Light. The 2 journals are supporting us, and we're still looking for more sponsors, so we will be announcing them as they come through. And with that, please apply. Thank you very much. Thank you, everyone. We really appreciate your attention. Thank you.